Hello, everyone. Today is my great pleasure to present our work at the ICSI virtual conference. And the title of our work is DeepBillBoard, Systematic Physical World Testing of Autonomous Driving Systems. So due to the advancement of machine learning techniques and the embedded system hardware, autonomous computing is a hot concept being pervasively applied in different domains. Here I show several: transportation, drones, robotics, and medical cyber-physical systems. So among these domains, autonomous driving seems to be a very promising application. So here I showed a state-of-the-art autonomous driving systems where we're utilizing a set of hardware to capture data and computing, analyzing this data through the Linux operating system and the robotic operating system middleware. And then we're applying state-of-the-art end-to-end driving application software like AutoWare as shown here. Okay, so basically what AutoWare does is for each captured image, it will utilize a set of DNN modules like localization, detection, trackings, which are mostly driven by deep neural networks. And then through analyzing the real-time captured environmental data, the computing system employed in this vehicle will be able to make control decisions like motion planning: should I brake, should I accelerate, or steering. So the deep neural networks actually is enabling such autonomy in driving to a very large extent. So here I showed an end-to-end driving, DNN-driven autonomous driving solution, which is first proposed by NVIDIA. So this solution, end-to-end method, is very powerful because by utilizing a set of CNNs and RNNs, the driving framework is able to kind of learn and mimic the behavior, the driving behavior of human beings under different road conditions. So because of the safety criticalness of the autonomous driving, so the robustness and safety testing, okay, becomes a very important topic, particularly given that recent set of research has shown that machine learning algorithms and DNN in particular are very vulnerable to adversarial attacks. So the result is that the DNN models, like for example steering, will not be able to make correct control decisions like the steering angle. So the goal of the robustness testing in software engineering is trying to identify adversarial scenarios. And indeed, there has been a recent rich set of works on digital world testing, where we try to generate digital world perturbations and to come up with artificial driving scenarios to enrich test suite. For example, the left three figures shown here is that where we generate digital perturbations and then apply it onto different road scenarios, and then try to come up with new driving scenes to see whether the autonomous driving system is robust under such settings or not. And some other recent work are trying to make such testing cases to be more realistic and diverse, like the two figures I show on the right-hand side. Unfortunately, what we have seen so far in this testing effort, it happens all in the digital world setting. So this is the major motivation behind DeepBillBoard, where we find a critical missing piece on autonomous driving testing, where we have to understand and exploit both digital and physical adversarial perturbation generation for impacting driving decisions. And in this paper, we focus on the steering module. So in other words, the digital world perturbation generated like we have seen here cannot be implementable in practice in physical world, right? There's no way for us to generate these small black dots and then paste it onto the sky, right? Which is our background imagery. So physical world, how to do physical world testing of autonomous driving systems is the major motivation behind DeepBillBoard. Okay, so we present the solution DeepBillBoard, which is a systematic physical world testing of autonomous driving systems. And in order to implement it in the physical world setting, DeepBillBoard targets at a very common and practical driving scenario where a vehicle may drive by roadside billboards. Like an example is shown here. It's very common for us to see such advertising space available on the roadside, and we can just call the phone number and then we run this space and we can put whatever contents or image onto this billboard, okay? So the goal is definitely to generate a single printable image which can be physically printed out and also pasted onto this roadside billboard target. And we want this single image to continuously attack the driving by vehicles, because again, the driving by process is a continuous process involving multiple image frames, not just a single frame. So there are many challenges, and I list which can be categorized into either physical world or technical issues. So physical world issues are very intuitive. For example, all in billboard area could be manipulated, right? So this is different from the digital world testing, where the entire image input, you can add perturbations to wherever you like, okay? So this is not possible under the physical world setting. Also, the background imagery is also moving during this driving by process. And also the perturbations we generate under the physical world, the methodology has to survive under different conditions, like lightning conditions, and also must be perceptible by the sensing hardware and printable, okay? So there are several key technical challenges, but a key technical challenge herein is that because the driving by process involves multiple frames, so all frames in this driving by scenario has to be considered in order to generate globally maximized attacking effects, because this is our technical goal, right? We want a single perturbation to continuously impact the driving by autonomous vehicles. So here shows a very general workflow of the DeepBillBoard, and details can certainly be found in the paper. So basically, we're trying to identify the coordinates of the targeted roadside billboard within each capture image during this driving by process. And then we feed this input into the DNN model, and we apply a joint gradient optimization algorithm, which is the key algorithmic component in DeepBillBoard in our design, to generate an adversarial pattern which can continuously impact the driving vehicle. Okay, so here is the general process. So we first, for each single image frame, we generate a locally best perturbation, and then we try to find a globally optimized single perturbation that would meet the DNN driving model the best in a continuous manner using this joint loss optimization method. And this method considers dynamic driving conditions and some other physical world dynamics. For example, this algorithm also enhances perturbation printability by transferring these RGB values to printable colors. So again, more details could be found in the paper if you are interested. So regarding evaluation, we have done a comprehensive set of experimentation involving popular self-driving models like the DAVE models proposed by NVIDIA, and know that these DAVE driving models have been intensively tested by NVIDIA by driving millions of miles and incurring almost zero accident. And we also test the another popular self-driving model, which is Epoch from the Udacity Challenge. And regarding the image datasets, we apply the Udacity, DAVE, and Kitty driving datasets, which are all popular and widely studied datasets for the self-driving scenario. And regarding the video datasets, we grab YouTube driving videos as well as the videos recorded by our own camera of a driving car when we drive by a roadside billboard on UTD campus when we conduct these physical world implementation and case studies. So here shows the digital world evaluation listing the predicted angle error under different data set and different road conditions. So here I just highlight 4 examples. As you can see here, we use DeepBillBoard to generate a single perturbation, a single adversarial image, and we digitally apply it onto the corresponding area of this roadside billboard. As we can see here, the predicted angle error is actually, the angle error is actually pretty noticeable, right? From 7 to almost 25 degrees. So as reported by the transportation agent sector, if the steering angle error becomes 3 to 5 degrees and lasting for more than 1 second, then this is considered as a very dangerous driving behavior, which may result in accidents. Okay. So regarding physical world evaluation, here I show 2 case studies where we print out 2 adversarial images and we print it out and paste it onto the roadside billboard, and we conduct this experimentation within the UTD campus. And basically, we drive a vehicle bypassing this roadside billboard, and we record the resulting angle error for each capture image frame. So this figure summarizes the results, where the x-axis denotes the frame index, the y-axis denotes the angle error. As you can see here, the angle error for all frame index are pretty noticeable, ranging from 5 to 10 degrees to almost 40 degrees. So here, an interesting observation is that whenever the frame index increases, the steering angle error also becomes larger. So this is very intuitive, because when the frame index increases, it implies that the vehicle actually drives closer to this roadside billboard. So this this adversarial billboard would impact the DNN optimization process a lot more compared to a far distance. Okay. So finally, I would like to show a video demo regarding how we conduct one of these physical world case study. As you can see here, we're basically driving on a straight road. However, the red arrow indicates the actual steering angle predicted by the DNN steering model in a real-time fashion within each image frame. So as you can see here, right? So the predicted steering angle is actually encountered a very large error compared to the correct steering angle, which should be just straightforward. Okay. Okay. Thanks a lot for listening to this talk. So basically, we present DeepBillBoard, a systematic physical world testing of autonomous driving systems, and a set of immediate future work we plan to conduct is to extend and apply DeepBillBoard using onto a set of realistic vehicles. Like right now, we're trying to implement DeepBillBoard using Tesla, and we're trying to see during an actual autonomous driving process, what is the efficacy of DeepBillBoard. Okay, thank you very much.